All right, so let's get back into section 7.2. So chapter 7 has been all about this idea of a linear transformation. So a specific kind of function that applies to matrix operations. And yesterday we talked about a lot of these different properties of functions and basically how we're now going to apply them to linear transformations. So, we kind of ended the last class with defining what all those things are, but now let's put them to use. So here's a linear transformation, and I want to find these three things. I want to find the kernel, the range, and the rank of this transformation L. So let's just go one at a time. If we start with the kernel, what is the kernel of a transformation? What does that mean? It's the null space. So L is a transformation. Specifically, it's a linear transformation. And the big idea from the previous section was that if L is a linear transformation, then I should be able to represent it with some vector, or some matrix A. So where this thing I printed out is written as, well, L is a function that acts on two-dimensional vectors. I should be able to replace that with some matrix A that when I multiply it by a two-dimensional vector yields, the output of this transformation. So in order for me to find the kernel of L, I need to find the matrix that is represented by A, so I can find its null space. So how can we find that matrix A? Should we talk about what order it has to be? So based on the product I have here, so the output is this 3x1 vector. I'm multiplying it by a 2x1. Has to be a 3x2. So A must be a 3x2 matrix. But what does that look like? So basically, if I fill this in and I multiply it by this column vector x1, x2, what will give me these outputs, the 4x1 plus 12x2, and so on? Let's take it row by row. If I know the top row of my output vector looks like this, 4x1 plus 12x2, then what should my top row look like of A? 412. So yeah, think about the way we multiply matrices. If I multiply this row 412 by the column x1, x2, I'll get 4 times x1 plus 12 times x2. So if we follow that logic, what does the rest of this matrix look like? 412, 515. So that's A. So given a linear transformation, we replaced it with a matrix that we can multiply by a vector and do all the same effects, get all the same results of our transformation. So as we've said, the kernel is the null space of A. So the kernel of L is the null space of A. How do I find the null space of this matrix A?
Reduce
Right, you can reduce it. That does a lot of valuable things for us. So if we do reduced row echelon form of A, what do we come up with? It should be, right, so I think the bottom two rows are 0, right? So I mean, all three of those rows are essentially the same. The coefficient on x2 is triple the coefficient on x1. So if that's what this reduced matrix looks like, what is the null space of A? Negative 3, 1. And to be perfectly clear, when we talk about the null space of a matrix, we're talking about building it out with a basis. Do I only need one vector? That should be sufficient. So I only have one non-zero row in this reduced matrix. And what does this row say? It really says that x1 plus 3x2 is equal to 0. Or if we solve for something, x1 equals negative 3x2. So I think the vector we wrote down there that's a complete null space. That basis has a single vector, and that's sufficient. So any questions on how we found the kernel? So the null space of A is equal to the kernel of the transformation that A represents. So these are equivalent ideas. Questions there? How about the range? What is the range of transformation? What does that mean?
All outputs.
All the outputs. So I mean that's essentially the same definition for any function. So I want to know what all the outputs look like. In terms of matrices, whether you realize it or not, we've been finding ranges for a very long time in this class, but we haven't really called them that. So if you treat the columns of a matrix as vectors that make up a basis, what are we really finding of that matrix? Yes, it's the range, but we've been calling it by another specific term for most of this class. What was that? It's the column space. I want to know if I treat the columns 4, 4, 5 and 12, 12, 15, if I treat those as, I'm going to say basis vectors, even though it's not really a basis. Why is it not really? Why are those two columns not really a basis? So 4, 4, 5 and 12, 12, 15. Yeah, if I triple 4, 4, 5, I get 12, 12, 15. So even if they're not a basis, they span something. I would like to know what they span. So how can we find the column space of A? What's that? It's a column of the pivot, which is 4, 4, 5, right? And in reality, you could use 12, 12, 15 as well, because like we said, they're identical. But the range of A, sorry, the range of L, which is equal to the column space of A. And really, it's an infinite number of things. So the way we're going to describe it is through its basis, which is a single vector. So we got the kernel, we got the column space, or the range. Questions on how we found those two things? What about the rank? I know we've talked about that in terms of matrices, and there's a few different ways to figure out what the rank of a matrix is. What's one of them? Column space or the row space? Specifically, what about the column space or the row space? The dimension. So it's how many vectors make up the basis for those things. So in this case, what's the rank of L? 1. So the column space has one vector in its basis. We didn't find the row space, but that would also have one vector in its basis. Those two things always have to be identical. So we figured out 3 different properties of this matrix. Where did they all come from? Like, I think we only really did one operation to learn all this stuff, right? What was that? Yeah, getting this into reduced row echelon form will typically tell you everything you want to know. But all these answers are different, so it's really important to know, all right, now that I've reduced it, how do I draw out of it the information that I'm actually asking you for? So questions on how we find the kernel, the range, or the rank in this case. All right, so now that we have those, let's talk about these ideas of L being 1-to-1 or onto. So talked about this at the very tail end of class yesterday. What does it mean for a transformation to be 1-to-1? Or any old function to be 1-to-1?
Well, honestly, well, like, I guess any function you said it reaches. Never mind. For 1x, there's only 1y.
So that right there, that's what a function is. So you've probably seen these like really basic like bubble maps for functions. Let's say the domain of this function is numbers and the range is letters. So since I'm saying this is a function that goes from the left-hand bubble to the right-hand bubble, then I'm allowed to do things like this. I'm not allowed to do things like this. So in a function, you can have things in the range that get mapped to from multiple things in the domain. So I'll give you here's a really silly example. This is a function, f of x equals 0. What values of x get mapped to 0 in this function? All of them. That's fine. It's a simple function, but it's still a function. I get one value of x. I plug it into this function. I get one value of y. That value of y just always happens to be 0, but that's still okay. But if I want this function to be 1-to-1, I'm not allowed to do things like this. Oh, sorry, no, that's a function. If I want this function to be 1-to-1, I'm not allowed to have things like this. I can't have outputs that get mapped back to two things in the domain. So for a 1-to-1 function, that means everything in the domain has to get mapped to something different in the range. Do we have that with L? How come? 2 rows are the same. That is a dead giveaway that this is not 1-to-1. One thing we can say for sure with linear transformations is this, and we didn't really talk about it, not specifically, but let's talk about what makes a transformation linear. And there are basically 2 rules that we have to follow. If a transformation is linear, then these are always true. L of v1 plus L of v2 has to equal L of. So I should be able to take the sum either before or after I transform and get no difference. That's a linear transformation. If I have a linear transformation, that's true no matter what v1 and v2 look like. The other one looks like this. If I scale a transformation, it's the same as me scaling the vector and then transforming that. What's kind of implied by these two is this. What happens if v1 and v2 are both 0? Well, that means you should just be transforming the 0 vector, right? Or if c is equal to 0, then you should just be transforming the 0 vector. So these 2 first bullets, they both kind of imply this third one that we haven't explicitly talked about yet, but that's this. If I transform the zero vector, I better get the zero vector back. I will point out that those zero vectors might have different dimensions, but that's okay. As long as everything in them is zero. Like for example, for this L, what is L of 0, 0? Zero what? But how many zeros? Yeah, so that's the thing I wanted to emphasize. It's 3 zeros. Because L takes two-dimensional vectors and maps them to three-dimensional vectors. So the zero vectors aren't always the same zero vector, but they're of the appropriate dimension. So why am I bringing that up? Here's why I'm bringing it up. Because if our transformation is 1-to-1, then are there other vectors? Like, is there some other vector that can be mapped to the zero vector? Shouldn't there? There can't be, because in a linear transformation, L of 0 is always 0, which means there can't be other things that also get sent to 0, that also get mapped to 0. Does our transformation have other vectors that will get mapped to the 0 vector? Right. So the fact that our null space has that basis means that you can, let's just take the vector from that basis. What is L of -3, 1? It better be 0, 0, 0, because we said that's the basis for the null space. So that means that 1-to-1 is not true. Because if it was 1-to-1, we wouldn't have multiple vectors in our domain that got mapped to 0. So questions on that idea of 1-to-1? All right, so what does onto mean?
In the general sense that a function that's onto everything that's like right.
Basically, it reaches like the maximum, it reaches everything in the range. So that's generally true. We're going to be very specific when we say onto. I want to know, is it onto Rn? You know, whatever the appropriate size, whatever the appropriate dimension space is on the output side. So for us, what's the dimension of our range space here? So it's R3. So yeah, you're right. The column vectors are always going to be 3 by 1. So really what I'm looking at is the number of rows. So I'll reword the question this way. Is L onto R3? What do we think?
Yes.
How come?
Because our column pieces and because R3.
It is. So our column space, it's a subset of R3. We need it to be all of R3. That's what the onto idea really says, that you can pick anything you want in R3. And if my transformation is onto, I should be able to take the column space vectors and somehow combine them to reach whatever you gave to me. So now, having kind of unpacked it in that way, is that true for L? No. So what is the basis for the column space of A? So the column space we found for A is 4, 4, 5. That single column. Is that a basis for R3? How do we know? There's actually lots of ways to prove that that's not a basis for R3. We are correct that it's not a basis for R3, but let's talk about how we can know that for sure.
Yes, the amount of what transformation we do to go for class can would be 1, 0, 0.
Okay, so the fact that you found something. So here's what you just told me. If I take a multiple of 4, 4, 5 and set that equal to 1, 0, 0, that can't ever happen. So the fact that you were able to find something in R3 that's not in my column space, that means that my transformation doesn't reach all of R3. That's enough to say that it's not on 2. If I have a basis of R3, how many vectors have to be in it? 3. Which means if I give you any other number, if I give you a basis of any other dimension, you already know it's false. So the basis for a subspace, those are never unique. I can adjust those a little bit, but their dimensions are always the same. Any basis I give you of R3 has to have 3 vectors in it, no more, no less. So the fact that I'm giving you a basis with a single vector in it means that it spans something. It's linearly independent because there's nothing else for it to depend on, but it doesn't span the thing that I care about. It doesn't span all of R3. So I mean, like, kind of like, I think about this last section here is like we're tying like all the concepts of the class, kind of throwing them all together. So I want to make sure that I'm taking that as slow as I need to. So with this one transformation, I asked you like 5 or 6 different things. I want to make sure we're okay with where we ended up. So to recap, we found the kernel, which is a basis for the null space of A. We found the range, which is a basis for the column space. The column space can give you the rank. And then from those ideas, we can answer those yes or no questions. Do we have a 1-to-1 transformation? Do we have an onto transformation? Any questions about any of that? Okay. Let's do another. So let's find bases for the kernel and range of this thing. Let me ask this question first. What is our transformation? What does it act on? And what does it yield? What does it map to? So what numbers go in those boxes? 2 and 4. This transformation takes in a 2-dimensional vector and it processes those 2 dimensions into a column that has 4 rows in it. So L is linear, which means I should be able to represent L as a matrix. What is the dimension, or what is the order of that matrix? Knowing that I can multiply A by x1, x2 to get this thing that I'll abbreviate y1, y2, y3, y4. It needs to be 4 by 2. So that's something we can kind of say in general. If we have a transformation that goes from Rn to Rm, then that means there's some matrix that is m by n that you can replace it by. Can we write that matrix now, knowing that it is a 4-row, 2-column object? What is it?
-5, 5, 5, 1, 3, 0.
Where did all that stuff come from?
So value. From, I guess, y.
Yeah, so what are the outputs equal? Y1 equals negative 5x1 plus 5x2. So knowing that I'm going to multiply A by x1, x2, it needs to give me these 4 rows. Then yes, I can simply pluck out the coefficients. So this is what A looks like. So I would like to find the kernel of L. How do I do that now? What can I do to A to find that kernel? So yes, you're going to reduce it, but then what do you care about when you reduce it? I want to find the null space of A. So after you reduce it, the bottom 2 rows at least have to be all zeros. What's the rest of this look like? One zero. Oh, so it's identity, and then okay. What is the null space of A? It's the smallest it could possibly be. How do we know that?
X1 equals 0.
Right. That's so the first 2 rows of this matrix that you've reduced to tells you x1 equals 0, x2 equals 0, which means the only way to, if you're going to multiply A by x1, x2 and get 0 out, the only way to do that is to multiply by the 0 vector. So my null space is minimal. It only contains the 0 vector. What's the range? What is the range of L?
Spaces.
So we're going to take, so you're basically saying that the range is just A?
Yeah.
Okay. I'm not disagreeing with you. I think you're correct. But let's talk about why. Why is that the range? Why am I just taking both the vectors? I didn't do that last time. What's that? There's 2 pivots, there's 2 columns, which means I need every column. The columns are linearly independent of each other. So basically the kernel and the range are, the kernel is the smallest possible thing. The kernel of a matrix always has the 0 vector in it. It might have more things, but it always has the 0 vector in it. And the range, we could not reduce the basis at all. Or not the basis, we could not reduce the matrix in a way to like eliminate a column vector from our basis. So we got the kernel, got the range. Questions on how we got this? All right, so now if I ask you, what's the rank? 2. How come? All right, so the rank of 2 is, rank of L is 2 because the column space had 2 basis vectors in it. Is L 1-to-1?
Yes.
How come? The null space is the 0 vector and nothing else. So yes, 1-to-1. Any 2-dimensional vector you could think of, if you take any 2 different 2-dimensional vectors, they'll get sent to different 4-dimensional vectors. So that's 1-to-1, and you can always tell that directly from the null space. If the null space only has that one vector in it, then everything is getting mapped to something different. Is it onto? Let's look through here. When I say onto what? Onto R4. We're saying no. How come? There's only two vectors in the basis. To even have a chance of being onto, how many vectors do I need to have? 4. So we could probably find a counterexample. We could probably find a 4-dimensional vector that I can't reach with those two vectors. At a 0, 8. That's not a 0. 0, 8, 2, 2. We could probably prove that that's not in the column space, but basically, if you add those two together, the first 3 rows line up, and I just intentionally missed the 4th row. Then we could probably prove that you can't combine those two vectors to get that. But even though we know there are counterexamples, the fact that we're offering 2 basis vectors to span 4-dimensional vectors is never going to work. It's never going to span everything. How are we doing? Okay. Let's talk about this idea of a fixed point. So we've talked about null space. So basically, what vectors, when you transform them, which vectors get sent to 0? Now I want to look at this. What vectors get sent to themselves? So what I'm looking for is this. I'm looking for the generic family of vectors that when I do this, x1, x2, x3, that gets sent to x1, x2, x3. So I don't think this is like anything we've done before. But any ideas how to start looking for these kind of things?
Find what A is.
We can find what A is. How do we find A?
A would just be all the values.
Okay. What's the order of this matrix going to be? Better be 3 by 3, because I'm taking in 3-dimensional vectors, I'm mapping them to 3-dimensional vectors. Should look like this: 2, 2, -4, -1, 0, -3, 2, 3, 8. So now here's what we've kind of replaced this with. We know that L is a linear transformation, which means that instead of talking about L of x equals x, I can say A times x equals x. So we've replaced L with A. Any ideas from here? How can we figure out what kinds of x's make this true? So this is we okay with this equation, by the way, that A of x equals x, or A times x equals x? What if I try to solve this thing? I'm going to try to isolate or move everything to one side. AX minus x equals 0. Am I allowed to factor out x? If I factor out x, what do I get? A minus, I don't want to say 1 though, because then I'm subtracting a, I can replace it with the identity. So let me do this first. I'm going to say AX minus IX equals 0. And then I factor out an x, I get x times A minus I equals 0. Does this look familiar at all? What does it kind of look like? basically I'm looking for a very specific eigenspace. So usually we hunt down like what values of lambda make this thing true. So ax equals lambda x. In this case, I'm not finding what lambda is. In this case, I am looking for, basically when I operate on certain vectors, I want to look at the vectors that don't get transformed at all. And the way we do that is substantially really similar to the way we find an eigenspace, except now we're dictating that lambda for us is equal to 1. So that's the rationale behind what we're going to do. So these are what fixed points are. If there's a vector and I transform it, it does not transform. It just remains the same. That's a fixed point. In these kinds of transformations that have fixed points, what can I say for sure about the order of that matrix A? So if I'm taking in vectors that, I don't know what they look like, they can be any size. But if it's a fixed point, what comes out the other side? It has to be square. How come? Right. So I am transforming vectors in one dimension. And even though transformations don't typically have to stay within the same dimension, if you're talking about fixed points, then you have to be. Because there is, in just an example, there's no way for this to be true. If I'm talking about equality after the transformation, I have to be dealing with something like this, Rn to Rn, which means the order of A better be n by n, or square. So the way we find fixed points basically come from, I'm looking for this specific eigenspace. X times A minus 1i, A minus I. This is what I'm trying to find. Questions on the rationale? Okay, so let's do that for this one. I think we said A was 3 by 3, which is already a good start. -2, 2, -4. -1, 0, -3. 2, 3, 8. So if that's what A is, what's the matrix I really want to deal with? I'm going to skip the lambdas because I know what lambda is. So you are right that you're going to be modifying the diagonal. But if we think back to the way we find eigenvalues, when we find eigenvalues, we don't know what lambda is, and we're trying to get that determinant, or we're trying to make the determinant equal to 0. In this case, I don't care what the determinant's equal to, because I'm more interested in the eigenspace for lambda equals 1. Go ahead.
So would it be, so you subtract 1 off the diagonal?
Yes.
So the negative.
Not -1. I agree. Now we're kind of relating this to, so even though these are not proper eigenvalues that we're going to find, finding eigenvalues requires us to figure out what those special values of lambda are. Let's think back to when we do find eigenvectors. How do we find eigenvectors? Which we've kind of done because we're forcing lambda to equal 1. So we have the new matrix we're going to find the eigenvectors of. We could, we don't. Well, so the determinant wouldn't tell us much. The determinant of this matrix is probably not zero, and that's okay. So let's talk about eigenspaces for a bit, just to kind of talk about the differences between what eigenvalues are and what this thing is that we're doing now. So eigenvalues are the values of lambda where this is true. So basically, lambda is a constant, x is a column vector, A is the appropriately sized rectangular matrix. Even though A is a matrix and lambda is a constant, these two sides are equal. So basically one of the ways you can think of what eigenvalues do is there are some constants out there that if I multiply them by certain vectors, it's the same as me multiplying the matrix by those vectors. So basically the matrix does nothing to the direction. The matrix preserves the direction as long as I make a very specific adjustment to those diagonal entries. We're not looking to preserve direction. Well, we are, but we're looking for something a lot stronger than that. We're looking to preserve direction and magnitude. So I don't even want to scale my vectors. I want to keep them just as they are. And in doing that, that requires the value of lambda we're looking at to be 1. So one more way I'll kind of point out the difference is when you're finding eigenvalues, you're required to figure out what lambda is. Usually has many, many values. When we're finding fixed points, that requires us to just say, all right, lambda equals 1. And that all comes from the kind of manipulation that I did a couple slides ago. If ax equals x, then that means that x times a minus I equals 0. So that's another thing I should emphasize. I want this product to be 0. So in this new matrix we wrote down, what am I trying to find with it?
We're trying to find what we can what we need to multiply a minus I to equal 0.
Right. So I want to find the vectors that if I multiply this by those vectors, I get 0. There's a much shorter name for that thing that you just described. That's the null space. So now that we have found the matrix A minus I, we are looking for its null space. How do we do that? Reduce. Always, I mean, okay, I don't want to say always, but there are so many things we do that are answered by finding the reduced row echelon form of a matrix. But we have to know what matrix we actually want to deal with. If we just deal with A, we're not going to learn what we want to learn. We'll deal with this slightly adjusted thing, A minus I. So what does it reduce to? 1, 0, 2, 0, 1, 1, and all right. Cool. If that's what the matrix reduces to, then what does its null space look like? What's x1 equal? What's that? Negative 2x3. Not simply negative 2. What's x2 equal? Negative x3, and then it looks like you're treating x3 like it's a parameter. So how many parameters do I need? Just 1. So the null space of A minus I is what? -2, -1, 1. So let's talk about, so I believe we're correct, but let's talk about what we just actually found. This basis vector right here, what is this the basis of? The null space of A minus I, and why were we finding the null space of that specific thing? We're trying to find the fixed point. So that means theoretically we should be able to do this. I should be able to multiply some matrix by -2, -1, 1 and get -2, -1, 1. So the last thing I want to be really clear on here is what matrix goes here. Not A minus I, but A. Let's make sure that happens. What is A times -2, -1, 1? Okay, so I feel good about it. This is a pretty simple one to check because we only got one basis vector. So the only linear combinations you could make of this vector are to scale it by multiplying it by scalars. I believe wholeheartedly that if you put a -10, -5, 5 in here, that would scale appropriately. I'm not going to make you do it, but I think we effectively found all the fixed points for that matrix. They're all the multiples of -2, -1, 1. How are we doing? Okay. It's the last thing I got for you ever. Not ever. Just do one more for the top. I want to find the basis for the fixed points of this transformation. So how do we start? Find A. Got to replace L with its matrix. What is the order of L, or sorry, of A? 4 by 4. So square is good. What do the entries look like? 3, -2, -12, 3. So we reduce this, right? Correct? No. Oh, I set a trap. Usually want to reduce the thing as is, but for fixed points, I want to find this. I want to reduce this more specific matrix, which is A minus I. What is that matrix going to look like? Or just tell me what changes. The diagonal, both diagonals? Just the major one that goes top left to bottom right. So 2, 6, 0, 5. Everything else. What's that? Yes. It's always, always, always -1. How come? Because now I'm not only interested in, so with eigenvalues speaking very generically, I want to maintain their direction, but I don't care if the vector gets longer or shorter. With fixed points, what am I requiring for a fixed point? Same size. So I want to scale it by 1. Basically, I want to keep its direction and I want to keep its length as well. So let's say generically a matrix has an eigenvalue of 4. Then what that means is you found this. I found certain eigenvectors that when I multiply them by A on the left, then I get 4 times V. That is an eigenvalue. That is an eigenvalue eigenvector pair. But fixed points are more restrictive. I want to find these. I want to find AV equals 1V. So because of that, it kind of saves me from looking for the eigenvalues because I'm looking for very specific behavior. So all of that explanation to answer your question, yes, I'm always just subtracting 1 from the major diagonal. So what is the reduced row echelon form of A minus I? 1, -1, -6, 0. Okay. What does that tell us? I don't agree with the last two things. Oh, wait, sorry. You're parameterizing. So it sounds like we're assuming at least 2 parameters. That's the very subtle thing in here that's important to notice. I'm not allowing x4 to take any value but 0. So basically what this says is that we do have some vectors that are fixed points. All of them have 0 in the 4th component. So now can we find a basis for the fixed points? How many vectors are going to be in it? How come? 2 parameters. I've already said that the bottom, the 4th component will be 0. What do the rest of the vectors look like?
The first one on the left would be
1, 1, 0, 0. 6, 0, 1, 0. How come? Where'd those come from? I agree with you, but where'd they come from? Right. So x2, where does x2 live in these 4 equations I wrote down? X1 equals 1 of x2. X2 is equal to itself. X2 has nothing to do with x3. And x4 is always 0. Plus x3 times x1 equals 6 x3s, or contains 6 x3s. X3 and x2 are independent. X3 is equal to itself. X4 is equal to 0. So now we have 2 different basis vectors for fixed points. So any combination of those 2 vectors will be mapped to itself by L. How are we doing?
That's not 2 on their own there. Fine.
Well, they could be on their own. So each one of those independently. So 1, 1, 0, 0 is a combination of these 2 vectors. It's one of these plus 0 of these. So that's a good question. So all the linear combinations of these 2 vectors includes the one on the left individually, the one on the right individually, any multiple of either one of them, and then any sum of those 2 things as well. But yes, if you were to take A and multiply it by 1, 1, 0, 0, what should you get? It better come back the same. If you want to verify to double check what we did, you can, but that's That's the basis we found. But like you can do whatever you want. This should also be a fixed point. 70, 0, 10, 0. No, 70, 10, 10, 0. But yeah, any of those combinations should get sent back to wherever you began. How we doing? All right, that's all I have for you. So what do we have left? 15 minutes? Okay. No, really go away. So I sent out an announcement last night, a couple nights ago, about kind of what's left. Who in here has had a chance to look at like the sample finals and all that stuff, or have you done that yet? Okay, that will be my unofficial homework assignment for y'all tonight, because tomorrow, basically, I think best case scenario, like I said, is for me to take it from you what is important to review on. So I'll come in, I'll answer whatever questions you have. We can kind of talk about the final in general. If you have questions about the format or kind of what's going to be on it, I think I've said that it's going to be technically comprehensive, but heavy emphasis on the last two chapters we talked about. What else? Oh, class on Monday. Here's what I think I'm going to do. So since we have a full day tomorrow to review, I think I'm going to tell you all not to come here Monday afternoon. What I'll do instead is Monday evening, I'll jump on Zoom for, I don't know, hour and a half, 2 hours. And if you want to jump on and ask questions, review stuff, I'll be there. But otherwise, let's do this. Let's have class as normal tomorrow, kind of review Q&A session. Monday, do not come here. Stay cool. And then Tuesday will be still 1 to 2:10, but that'll be the final. Make sense? I will send out an announcement, but do not come here on Monday. Tell everyone you know, don't come here on Monday. Yeah, I'll go ahead and let's cut this early. I'll stick around for a bit if you have questions. Otherwise, I'll see you tomorrow.